right, so I'm going to go ahead and share my screen first. I have a bunch of stuff that I want to show that will give more context for any viewers that are watching. All right, cool. So right now on the screen, I have up the new, or one of the new Clarity 4 functions. This one is called SECP256R1 verify. And essentially the purpose of this is to allow anyone using any kind of, I guess, authenticator that's using this crypto curve to verify signatures in Clarity contracts. And I know this was publicized a lot over the past few months thanks to one of our community devs named Rafa. He was the one that originally proposed this earlier this year, which eventually got confirmed for the new SIP31 upgrades and in Clarity 4. But yeah, this function right here. You can check it out in our Stacks docs under the reference section. And yeah, so we're going to be talking about this function today, and we're going to be talking about the specific crypto curve behind this function. Right, that's better. I put it on light mode. Yeah, you guys let me know if it's too bright or whatever, but I usually prefer light mode in demos or workshops or whatever. But yeah, so Joey, give us a high-level overview, or let me back up a little bit. So Clarity functions, this function right here, it verifies a signature that used this particular curve, SECP256R1. Now, Clarity already has a verify or recover method for another crypto curve, and that crypto curve is called SECP256K1. So it's very similar. Literally, it's just one character difference, R1 versus K1. And that curve, obviously, it's pretty well known within the crypto and Bitcoin ecosystem. I think anyone that's new to Bitcoin or new to crypto, a lot of the first things that they learn in their, one-on-one primer is this particular curve, just because of its relevance and prevalence in Bitcoin and crypto. SECP256K1. Let me actually pull it up, see if I can find the methods. Yep, right here. So SECP256K1, this curve, it's used to generate a public key from a private key, and it's the particular elliptic curve standard behind that generation or derivation. And then so this other curve, SECP256R1, this to me was kind of new. I never heard of this curve before until this year. And so I'm sure a lot of people that are watching this are also unsure of what R1 is or how R1 differs from K1. K1 is obviously used in Bitcoin and Ethereum and a lot of other crypto networks for public key generation. So yeah, Joey, if you can give us like a high level overview of what is this R1 curve and explain the high-level differences between R1 and the K1 curve.
Okay, so the R1 and the K1 curves come from about the same point in history. They're all from about the year 2000. They both are what we call Weierstrass curves, which means they follow a very simple equation. Y squared equals x cubed plus ax plus b. So you notice there's an a and a b parameters for each of these curves. And that's the only main difference between these curves is what the parameters are that define the curves. It's just an algebraic equation, and certain numbers will define these curves. So the R1 curve is a product of the National Institute of Standards and Technology, whereas the K1 curve is not. It's a product of the Standards for Efficient Cryptography group, which is an international kind of more broadly spaced, whereas the National Institutes of Standards and Technology is a U.S. organization. So these are the two curves, and they also have, like all elliptic curves, they have a field size. The field is just the numbers used for the x's and the y's, and the field size is just a very large prime number. And these two curves have a similarly close but different prime number that defines the field size. And they also have a slightly different thing, which is called the group order. And a group order is how many actual pieces you have inside this group. How many times we can iterate through this equation and find a different value. How many different elliptic curve points there are to play with here. And these numbers are all about the same. They're 256-bit wide numbers, but they're slightly different exact numbers. So these are the high-level differences between these two groups. They're roughly the same period of time, roughly the same equation, but the specific parameters that form the equations are slightly different. And that's kind of the high level difference between them.
Okay, let's unpack that a little bit. So I have my whiteboard right now. I'm just jotting down some notes just so I can help to visualize differences.
So that's actually the SECG, not SECP.
SECG. Okay. Okay. So on the left, we had the K1 curve. On the right, the R1 curve. This is the shared formula that both of them share. Y squared equals XQ plus AX plus B. But you're saying that the K1 curve are using the coefficients for A and B as 0 and 7, correct?
That is correct.
And then on the other hand,
on the R1, it will be -3. And then the B value is a little more complicated. What they did was they took a series of bytes and they hashed those bytes through SHA-1 and converted that to an integer. And that's what B is. So it's the SHA-1 hash of just a particular sequence of bytes.
gotcha. Okay.
And that, when we segue into the next section, will be very relevant.
Okay. So, let me just continue back, just unpacking what you explained just before. So, NIST standard versus the SECG standard, from what I understand, is that the NIST standard is almost like the government or formal standard for like enterprises and governments. Is that correct? And then the other standard, SECG, is more for like open source cryptographers.
Basically, yes, except the NIST standard is specifically an American government. This is the American standard by the American government for American government use standardization. And because it's from the American government, it takes input from the NSA specifically, which the SECG group does not at all. The SECG group is, like you said, it's open source cryptographers. It's worldwide. It's academic. It's not government.
Gotcha. Okay. I mean, just with that statement, I can already see like the conflicts of interest between both groups. And then so let's focus on this formula for now. This is, I guess, to what you referenced before. This is part of the Weierstrass curves, and I'm assuming this is like a standard curve formula for that particular curve.
Yep. All Weierstrass curves have this general formula. The only thing that differs is the A and B parameters and what the actual different field sizes for the numbers are. What prime numbers we use to say how big of an X and Y can we have and how many points there are on this curve.
Okay. And so to confirm, K1 started first, is that correct?
So if you look at the history, they both started about the same time. They're both around the year 2000. One shows up in a draft of an ANSI standard around 1999, but it was standardized by NIST in 2000. And K1 is from about the same period of time. It started being talked about around 2000. Its formal specification was pretty much identical in time. There's a year here and there where things are bouncing around between specific formalizations of standards. But in terms of the history of cryptography, they are basically peers.
And so the question I'm sure a lot of people are thinking of right now is, well, then why does Bitcoin use K1 instead of R1? And then why doesn't, I guess, NIST or the governments use K1?
Mm-hmm. And that really is the elephant in the room here. So why did Satoshi Nakamoto decide not to use R1? R1 was, if anything, more widely used throughout industry, but there was an issue with it. So if we backtrack a little bit to the 2000s, we had a series of disclosures about cryptography and about how the American government interacted with standards in ways that were seen as nefarious. There was a, just like a random number generator. It's called the dual EC DRBG. It gave you a deterministic sequence of random bits. And this was thought soon after its release to possibly be a backdoor, possibly thinking to be a Trojan horse by the NSA to make it so that they could predict random numbers that would allow them to steal people's TLS sessions, things like that. It basically would allow the American government to spy on people. And the reason why they thought this was a couple of reasons. First of all, just like we see in SECP256R1 with the B parameter, where it's just the SHA-1 hash of some random number, the dual EC DRBG also had a number which was similarly a hash. It was just a large number, and no one knew where that large number came from. And in cryptography, we have this concept of a discrete logarithm. This is what protects all public keys and private keys. We have public keys, but these public keys are backed by a private key. And we have this way of saying, okay, like if we're doing elliptic curves, we'll have a private key, we'll multiply some point by that private key, and that becomes our public key. The idea is that it's easy to do the multiplication, but it's hard to do the opposite. It's hard to take what's called a discrete logarithm. We view these as one-way functions. You can reverse this, but it takes brute force methods, and these brute force methods would take until the end of the universe in order to calculate. No matter how fast we made our computers, no matter how much we try to make it parallel, thermodynamically, you cannot make a computer fast enough to reverse one of these things in a reasonable amount of time. But if you just have this curve point and you know what the number is that you multiply by a base point to get this point, then you have hidden information. And that's what they realized when people started dissecting this dual EC DRBG, was that they had this P parameter and a Q parameter, and if it turned out that you knew what you had to multiply P by to get Q, this algorithm was completely broken. And it's interesting because you might ask, well, could they have done a different algorithm? And it turns out they could have. They could have made a couple of very simple changes to the algorithm so that even if you knew what Q was relative to P, it wouldn't matter. And they specifically did not. And when cryptographers pushed back against this, the NIST said, no, we're going to keep it like this. They were very specific that they wanted to have this algorithm, which was vulnerable, demonstrably vulnerable, if you knew what the secret number was. And then lo and behold, a couple years later, Edward Snowden releases a whole bunch of NSA files. And in those files, they specifically said, we know this number.
Wow.
And we have to make sure we keep this algorithm broken because we know this number. And now that we know this number, if we see any random number generated by this algorithm, we can predict the next number in the sequence. And not only can we predict the next number in the sequence, we can predict it faster than someone who's actually running the algorithm. So they can know what your next TLS key is going to be before you know it, which was just horrifically bad from the perspective of people around the world who wanted to use cryptography to have things secure. So because of all this, when the Bitcoin system was being created, people looked at SECP256R1 and they said, oh, wait a minute. This also has this number, this B parameter. And this B parameter is the hash, and it's the hash of just some random sequence of 20 bytes. Where did these bytes come from? Do these bytes also contain a secret hidden trapdoor that's going to allow people to be able to do something nefarious with this curve? And after a bunch of research later, there have been a couple of ideas about how this might happen. And it turns out that for elliptic curves, you can use a weak curve to actually reverse this hard problem, this discrete logarithm that I said underlies all efficient cryptography. If you have a curve that is known to be weak, and if you know precisely how it is weak, you can take these discrete logarithms in a very short period of time. And so that was the fear with the SECP256R1 curve, was that this unknown B value, or the value is known, but how they arrived at the value is not known, and why they chose that value was not. And academically, there were discoveries that said, yeah, if they chose this value to make it to be a specifically weak curve, then this entire thing is broken for them specifically. And which would mean that the NSA could steal your Bitcoins. They could steal your private keys. They could impersonate you. They could sign things. They could pretend that you signed something that you didn't sign. Whereas the SECP256K1 curve, you notice that these numbers here are 0 and 7. They're very simple. So there's no way that you could just try a whole bunch of different curves and come up with 7 and figure out that 7 happened to be weak. This is why for R1, it takes a SHA hash of some random byte stream, because the idea is they could have looked at a whole bunch of curves, millions of curves, billions of curves, and just found that one that happened to be weak that looked random but was not. And so with the K1 curve, since the parameters are very simple, 0 and 7, there's no way they could have applied this process. They couldn't have searched for billions of ones and found that the number 7 just happened to be weak. So this is why we're having this discussion. This is why K1 is used in Bitcoin and all of the cryptocurrencies, or most of them. I don't know of anyone that doesn't use, I don't know of anyone that does use R1. There are ones that use other modern curves, which are also not thought to be dangerous. But this is why we use K1 in Bitcoin. And this is why R1, even though the National Institutes of Standard Technology is a very respectable organization, and even though you need to use this curve if you want to interact with people who use the Federal Information Processing Standards, Bitcoin chose not to use this curve. And when we made Clarity, we chose to support the K1 curve because that was the curve we were already using in order to interact with Bitcoin.
Wow. Okay. There was a lot exposed there just now.
That's super interesting.
Kenny, I'm sure you have a lot of questions. I'll let you go first.
Well, I think one thing that I wanted to do before we dig into that specifically a little bit more, for anybody that's watching that's not super familiar with cryptography, I would include myself in this category. Can you kind of explain exactly what you mean when you say an elliptic curve and how that relates to this equation and these numbers? Like when you say, for example, there could be a weak curve. What does that actually mean? Like what is happening in the math that's related to this equation and these numbers when you say an elliptic curve?
So that's a very good question. Unfortunately, I'm going to have to get a little technical to answer it. I will try to keep it on a generic level, though. So an elliptic curve in general is just like in algebra, you have equations, and equations make graphs. And we see an equation on the screen, and so this equation makes a graph. That means that for certain values of x, there will be certain values of y. And this is how we create what are called elliptic curve points. And elliptic curve points follow certain rules. You can add these points together. Just like with any what mathematicians call a group, there's an operation you can do on it. And that's how we use these things in terms of cryptography. So the question you're asking, though, is what would make a curve weak? And it's actually pretty complicated. The idea is that we could take, if you have a curve that's known to be weak, we can embed it in what's called a pairing curve. These are curves, the same kind of curves that you use, for example, for ZK snarks, for Groth16. These are curves that kind of mix two different curve points together. So if we can embed a curve equation into this kind of paired up curve point equation in a way that's very simple, we can use the simplicity of this embedding to reverse this process of taking a discrete logarithm, or reverse this process of multiplying a curve point by a large number, which is the same process we do to make a private key into a public key, which means we can find a public key and we can find the private key behind it, which allows us to steal people's money, sign things for them. But it's just this strange process of taking this curve and embedding it in this other kind of curve that mixes two curves together in such a way that we can use that embedding to solve this problem on the first curve in a way that's much faster than would be by just trying to brute force it.
Okay, cool. Thank you. So this SCP-256R1 algorithm, is that when you were talking about how it turns out that if you were able to know what this number was, you would be able to basically solve the curve faster than anybody that even just like has the typical public-private key pair. Is that currently the state of the R1 algorithm?
So that I was talking about the random number generator that was found. That was the source of all the fear and loathing around this curve. It was that random number generator that there was a secret number which was known. Here we know the secret number. We know what the B parameter is. We just don't know why it was chosen.
Okay.
So, but with the random number generator, there was a secret number which was known to the NSA and nobody else, which allowed them to predict the random number sequence faster than you could generate the random number sequence.
Okay.
And it's because we know that existed that we are afraid of the B parameter here.
Because there is no real transparency around why that particular number was chosen.
Exactly.
Okay.
And we know that you could follow this process to create a B parameter, which gave you a weak curve, which would allow you to take discrete logarithms, which would allow you to steal people's money and impersonate them.
So ever since, I guess, this controversy of this B value that is just some random SHA-1 hash, which possibly could be from that controversial random number generator, has the NIST ever addressed this value?
No, there has never been any explanation for why they chose this value.
Interesting. Wow.
And so if we go back to the K1 curve, there's no question of why do we choose 0 and 7. We choose 0 because it makes the curve even simpler to evaluate, and 7 because it's a nice short prime number that no one thinks there's anything hidden inside of it.
And it's so, if this is a known controversy and still a known question mark of this random B value that nobody knows about, or nobody knows how it's generated, how did R1 become such a standard amongst all these like different tools, enterprises, companies? Is it because it follows the NIST standard? And is there some kind of like policy where certain technologies need to follow the NIST standard?
That is precisely what it is. It is an NIST standard, which was formalized as a FIPS standard, Federal Information Processing Standard, which means that if you want to interact with the federal government, you have to use a FIPS standard. This is a requirement by law in order to interact with these organizations. These are non-military, but government organizations. If you want to interact with them, if you want to have a digital signature, if you want to connect to their servers using TLS, you have to use the FIPS specified standards. And the idea was that these standards would be more secure. They would be, the government would standardize on very secure things, which is why it's so egregious that this trust has been lost due to that random number generator, which was found to have a backdoor. It used to be that people thought, oh, that meant that this was a good one. This meant this was better than just something created by random cryptographers and academic people around the world. But it specifically is because this NIST standard is also formally a FIPS standard, which means you have to use it to interact with government.
Interesting. Yeah, this is all new for me. Wow. And then so if a company or enterprise refuses to use R1, then they couldn't use any of the government services or operate as a normal, I guess, recognized business by the government.
I mean, you can operate as a recognized business, but you can't do business with the federal government. And there are certain industries where you would need to use a FIPS standard, like for healthcare processing and keeping like data safe kind of things.
Okay, interesting. Does the U.S. military have to follow the FIPS standards?
No, the U.S. military has their completely own separate things, which are not known or widely used by anyone else.
Interesting.
This is for non-military government use. Having said that, I don't know what they use, and they could well use it, but this is not specified. But we don't know what they use. They can use whatever they want, but if you interact with non-military government, you have to use these.
Okay, interesting. Yeah, that was very insightful, actually. Kenny, do you have any more questions on that?
I think I'm just interested in like the specific reasons why somebody would want to use R1 over K1. And it sounds like it mostly comes down to if you need to interact with the government in some way, or if you need to use some sort of other existing standard that relies on R1, which like an example for that would be like this WebAuthn protocol. Is that correct? Which then that is how you would be able to do authentication, like hardware-based authentication or like biometric authentication. Is that, am I getting the connection right there between R1 and WebAuthn?
Absolutely. Yeah, that's absolutely correct. Once there's this need for people to use these curves to interact with government, that means that the software suites all support this curve. And since this all the software packages support this curve, then it just kind of finds itself being used in contexts where it wasn't strictly speaking necessary from a legal point of view. But then, like you said, this standard is built off this other standard. And so they just specify this because it's in the other standard. And then it just finds itself being spread farther and wider, even in contexts where it's not strictly speaking necessary, just because it was already so widely used.
So to kind of wrap up and put a bow on the controversy part of this, the controversy centers around the fact that there was this known backdoor in this random number generator. And because of that, any lack of transparency around an algorithm is going to be met with skepticism. And it's not that we don't know what the B value is, it's that we don't know why they chose it. And so there's just some unknowns around that. But there's no, as of now, there's not like a known way to break the R1 algorithm or anything like that.
That is exactly true. No one has ever been able to prove that the R1 algorithm is broken, and people have tried. People have tried a lot over the years, ever since. It's been almost 20 years since this started to be a concern, which is why the attack that I described, where you take the curve and you embed it in this paired up curve, that's the only attack which is thought to be possible these days. There were other possible attacks which, had they been actually the reality of what was going on, we would have been able to figure it out. It would have been that we would have figured out, oh, not only is this attack possible, we've found how to do the attack. But we never found any of the simpler attacks to work, which means they probably aren't what's going on. But this much more complicated attack is still possible. And like you said, it's only because of the lack of transparency around how we generated this value. And because the previous time we had this lack of transparency around a generated value, it was in fact found to be
interesting.
So WebAuthn, a lot of hardware devices, they're using R1 to be compliant with the FIPS standard. Does that mean, that doesn't mean that they can't also support K1. Is that correct?
Yeah, you can any standard you can support whatever you want to support. But if you're going to interact with the federal government, and if you want these things to be used by default, then you would want to have the R1 curve be your default. And also there's a thing with hardware where hardware doesn't like being upgraded. So if when you create these hardware tokens, if you create them using R1, then that's kind of it. Everything that interacts with it's just going to expect to use R1. You can't upgrade the hardware on these tokens once they're in the wild. And so you just kind of get this lock-in kind of effect where we have this, we did it this way because we need to do it this way. Now everyone else is doing it this way, so we're all just going to do it this way. Unless you have something like cryptocurrency, which is a whole new thing starting in the late 2000s. We get a chance to do a greenfield because this doesn't exist right now. We get to choose whatever we want to do, which is why they had the option and took the option of choosing K1 instead of R. There was no legacy cryptocurrency system to interact with because there was no other cryptocurrency. So they got to have a greenfield choice, and they chose to not jump into this possible can of worms.
Gotcha. Interesting. Yeah, that was all super interesting, and it gives a bit more context as to why there is a K1 and an R1 curve. But yeah, I guess to transition, with the support of R1 in Clarity contracts, we've already added support for R1 in Clarity, I think starting a few weeks ago. To transition, how or what was the design or decision process in determining what kind of R1 library or standard we should be using in Clarity?
So I was actually in charge of that effort, and we had basically 3 criteria that we wanted to find a library that fit all these 3 criteria. First criteria was that it was pure Rust. It was just Rust code with no unsafe Rust blocks, no underlying C library that could be vulnerable. We wanted a pure Rust code implementation. Not only did we want it to be pure Rust, we also wanted it to be a pure Rust implementation that had been audited. This was crucial. And furthermore, we wanted a pure Rust audit implementation that was also widely used. And if you think about it in terms of these 3 criteria, there was exactly one option out there that fit all 3 of these criteria. And it's from a very well-known, very respected group of developers called the Rust Crypto Group. And they implement all sorts of elliptic curves. They implement all sorts of algorithms, signature generation, verification, basically. And they also implement general arithmetic, which has been useful for if you're doing any kind of custom things like the things that I've done in my time at Stacks Labs and Trust Machines before that. But so it's just a very well-known, well-respected group of cryptographers who have pure Rust implementations of all these curves. These are audited and they are widely used. And that was the criteria. And there was no one else was even close in terms of available implementations of R1.
Gotcha. Okay, interesting. Yeah, right here, what we're looking at is the actual implementation of the new method in Clarity. Right here, it takes in 3 arguments. It has a bunch of check statements to make sure that the arguments are typed correctly, which then gets patched to that library that we were talking about. And then so with this as well, so you're saying this new library, Rust Crypto library, it's supporting both the R1 functions and the K1 functions. Is there, I think you might have alluded to it before, but is there any differences in like calculation speed that we should be considering or worried about? Or
between R1 and K1?
Yeah.
Or between the different libraries?
Between the different libraries.
So for R1 and K1, there's both a difference in speed of execution between the curves, and there's also different speed of executions in between the libraries. So for the Rust Crypto implementation that we went with here, the Rust Crypto implementation is very well structured. It's very clean. It's very secure. There are certain things, though, that it does where in terms of speed of execution, it is not as fast as the Bitcoin's SECP256K1, because SECP256K1 is very optimized C code, which also implements a couple of advanced algorithms if you want to do very large mathematical operations. However, these large mathematical operations are not relevant to our use case at all. So whether we use whether we use the K1 implementation from Rust Crypto or whether we use the C code from Bitcoin, it doesn't really matter for our use case. All we're ever really doing here, we're just creating and verifying signatures. And doing that is going to be essentially the same speed, whether we're taking Rust and piping it into a low-level C library like the Bitcoin's libsec-p256k1, or whether we're going to the very well-structured K256 from the Rust Crypto people. But in terms of the libraries, in terms of the differences between the curves themselves, as we saw in the other, in your whiteboard, the K curve has a 0 parameter for the A value, which means that when you evaluate this curve, you have to do a few less operations. So K1 will always be a little faster than R1, given a similar implementation. But again, the difference is fairly trivial.
Gotcha. To kind of wrap up this R1 versus K1 segment here, I guess for you, as a cryptographer, do you have a special curve that you have like a high interest in, or like is there a curve out there that you admire the most? Or
So I have always loved the K1 curve. I love the K1 curve because of the simplicity of the arguments, because of the speed of execution, because of the very fast implementation in Bitcoin. So in my times at Trust Machines, I worked on weighted aggregate threshold signatures. This is a way that you can create a key that underlines a Bitcoin wallet. You can split it into an arbitrarily large number of pieces. You can have people who hold different quantities, different numbers of shares of these keys, and they can efficiently construct keys, rotate keys, and make signatures which aggregate. So an aggregate signature means you might have 100 people forming a signature, but it squishes down to one single signature on the blockchain. And this is really beneficial because for traditional multi-sig approaches, if you wanted to have multiple people signing something, you had to have multiple signatures on the blockchain, which meant that this doesn't scale because every signature takes up more space. The more space you take up, the bigger your transaction fees are. And there's also hard limits on the size of a transaction that will fit into a Bitcoin block. So if you have an aggregate signature, though, you can scale as much as you want to. You can have thousands of shares of the key controlled by hundreds of people, and it all squishes down to a single signature. So long story short, the C library that Bitcoin exposes, the SECP256R1, has special algorithms that let you do these large operations with a logarithmic speedup, which means that you can basically do it in a reasonable amount of time. So I like the K1 curve because it supports these large algorithms, specifically in terms of the implementation in Bitcoin. A lot of cryptographers like a different curve, though. It's called the curve 25519. And this curve is a very recent curve. It's a recent creation by cryptographers. It has no ties to any government groups or anything, so it's also thought to be secure. And it's something I've used it in other cryptocurrency contexts and other jobs that I've had. It's kind of like the new shiny, whereas the K1 is the old kind of not so much crusty, but it's been around for longer and it's not new, it's not fresh. So with the curve 25519, it's kind of a way of taking a curve which doesn't have a prime order group and then making it prime order by default using this thing called ristretto encoding. And this curve is thought to be faster. It's roughly as secure, but it's basically just a new thing that a lot of people like to use instead. But me personally, because of the work that I've done, I've always been fond of the K1. You can't beat 0 and 7 as parameters in an equation.
It's almost as if like K1 has given the title of being the OG curve.
It is. In fact, when it comes to a cryptocurrency context, that is precisely what K1 is.
Yeah, awesome. To be honest, I'm going to have to watch this recording back and really grok all of the information that you shared this morning. Those were all the questions that I had. What about you, Kenny?
I think the one last thing is just from like a practical implementation perspective. What if, as a developer, what would I actually need to build if I wanted to say like integrate something like Touch ID or Face ID or any of these like things that use WebAuthn? What does this new function handle? And then what do I actually need to do as a developer to build on top of that to actually get that to like be a good user experience all the way through?
So as a developer, you would have to basically use these hardware, other external kind of scenarios, tokens, dongles, whatever. You're going to use these things and they're going to give you just a digital signature, an ECDSA signature that's based on this R1 curve. And so what you can do is if you have one, you can write a Clarity contract that basically validates that you do have a valid signature on this curve. And so your user flow would be something like, here's my public key, and then I'm going to be able to authenticate that the transaction that I'm sending into this contract has been separately signed by this piece of hardware. And then you can create some sort of automated flow that says, hey, I'm going to register myself on this contract with this public key, and then I'm going to interact with this contract using some sort of authentication layer, which depends on this curve. It's going to give you a digital signature based on this curve, and then the contract will be able to verify that this was in fact you who used this piece of hardware to generate this signature on this curve. And that's why we have this function.
Okay, cool. So I'll be kind of handling the actual signature itself separately. I'm just passing that signature into this function so that then I can go through, execute whatever clarity functions I need to based on confirmation that that public key matches that signature that the person passed.
Exactly.
Okay.
That is exactly it.
So it's almost as if like the credentials that WebAuthn will be providing for users, such as the signature, public key, and whatnot. It's almost as if like that is the actual wallet for the user.
Yeah. So, when we're interacting with a Clarity contract, we have to have some sort of Stacks wallet in order to send transactions on the Stacks blockchain. But the content of those transactions can be anything. You can just throw a whole bunch of opaque data into a Clarity function and say, hey, we're going to feed you this signature. And so it's completely separate to how Stacks authenticates the wallet who made the transaction. The payload itself can be separately authenticated using this other format, and that separate signature, which would just be part of the payload of a Stacks transaction, which we call a smart contract function, would be separately authenticated. So you would have this contract that some person would deploy this contract, other people would call this contract, but the contents of what's inside those calls can use separate authentication, and that's what will be tied to these external kind of things. It won't be your Stacks wallet that's tied to your WebAuthn, to your hardware dongle. It'll be some separate wallet, or some just separate cryptographic system that's being evaluated inside the payload of these contract calls to see that you really are you to do whatever you want. This is the whole, this is why we have DeFi. This is why smart contracts exist, is because you can do anything with them. And it's just a general programming layer. You still have to interact with it using a Stacks wallet because that contract is on the Stacks blockchain. But what you put into that contract, what you're evaluating, what you're trying to say, who you're trying to authenticate to do what, that's entirely up to the developer. And the sky's the limit. And now that we have these signatures, we have a whole different set of things that we can interact with. And our developers will have their work cut out for them because now they can do so much more newer and interesting things.
Awesome. Perfect way to end that segment there. Awesome. Well, thanks again, Joey, for
Thank you so
all
much
that
for having
information.
me.
Yeah, for sure. For the rest of this live stream, me and Kenny will just kind of go over some updates and some recaps of the Hacker House the other week. So yeah, if you wanted to stick around, you can. Or if you want, you can also just hop off now. But yeah, thanks again, Joey.
Thanks, guys.
Yeah,
Take
thank
care.
you. Appreciate it.